All right, the second row, let's say V1 is from, if we label here to be 0, here to be 1, here to be 2, we can label that, right? 0, 1, 2. What is this? I couldn't see that. Tiny. Yeah, it's going to be 0 here. So that will be too small. So V1 is from where to where? So when you are labeling the two terminals of V1, a voltage supply, you are starting from the higher potential to the lower potential, because that's a voltage drop of that voltage source, which is 5 volts, right? So the 5 is a 5 volts DC power supply, and the voltage drop is from 1 to 0, which is 5 volts. So you want to start with 1 and then 0 as a DC and 5 volts. And next is R1. You can say R1, smaller case as well, doesn't matter. R1 is from 1 to 2, and it's 3K. And then R2 is from 2 to 0, and it is 2K. And now we need a SPICE code. Let's see what's on the problem. There's a SPICE code in there. So calculate the current and voltage V out. So the first task is just write the code, and the second one you are going to do the simulation. So we can do first one, the second one together at the same time. So current, calculate the current and voltage using Ohm's law, right? Just manually calculate it. And verify the calculation using both simulation and the multimeter measurement on the board. So you need to build up the circuit and measure that, and compare to the simulation result and the calculation result. So now let's see the simulation result. So we are trying to probe where? The current and the voltage V out. The current will be whatever current, for example, the current flows through this resistor and this resistor and this power supply. They are sharing the same current because this is just one branch. So we can directly use time domain analysis, like we are directly connect this current meter in or voltage meter to a oscilloscope. So we do dot tran, which is transient analysis in time domain, from 0 second and stop at 1 second. And every 0.01 second, we plot the point of the curve. So for example, that's this circuit using the first method. And now I start LTSpice, and I go to open, I go to desktop, and I find out that specific text editor, and I open that in here, and I run simulation. So what are the signals you want to probe from the website compared to your calculation? The current I and the voltage V out. So the voltage V out in our circuit, it is actually V2. So go to here, right click, add traces, V2, and that's V out. And you need, when you are presenting this in your lab report or similar stuff in your homework in the future, you want to shrink, resize this window, and to make it smaller. You don't want to, you don't, since it's a DC, it's a flat signal everywhere. You don't have to show like this long. You can make it smaller and put the monitor beside this curve. Highlight the one you are interested, and then do a snapshot for these two. So you are showing the curve, simulation curve, and you are showing the final result, and you highlight it like that. For this one, if I don't know if you can make the 3 parts in the same figure. I probably don't do that since you don't have space to put them together to make one snapshot. It just looks not really nice. But if you have a figure like that, you can save it and put on the report later on. Okay, so that's for V out. It's 2 volts. And now let's see if it's making sense. It's 2 volts here. Can you know this is 2 volts by just calculation really quick? You total have 5 volts for the entire voltage drop, right? And this 2K has, so the resistance share equals to the voltage share. So this guy is sharing 2/5 of the entire resistance. It's 2K, 3K, so it's sharing 2/5 of that entire resistance. So it's going to be 2 volts, right? Resistance share equals to the voltage share. It's a voltage divider. So that's the first way you make a circuit in LTSpice. The second way, you just copy the same spice code, but without the first line. You close this, go to start with a new schematic from here, and then go to File, Save As. You just save it to desktop. You say task1_1, for example, and save it. And go to .op, click, paste, and OK, and put it here, and run the simulation. You're going to get the same plotting monitor, and you can add traces from there. And now let's see the third one, which is the easiest one. So you start with a new schematic as well, and you save it as task1, 2. So there are a few shortcuts. I've been using all the shortcuts all the time, so I forget where are the traditional way to do that. So you want to open the library to bring all these components from the library, the components. So you press F2 to start the library and move the scroll bar to the right, pick up voltage, click OK. You can place the voltage power source over there. And if you do not press Escape on the keyboard, you are going to be able to place more similar one, not the same, exactly the same voltage, as many as they want. I can place a lot, but I just need one, right? So I'm gonna press Delete on the keyboard, so show up a Caesar for the cursor for my mouse, and I will select this area because this area I want to delete all of them, so I can cut and cut, and I press Escape to quit from that Caesar's mode. Please come to the lab on time in the future. Not, I mean, don't mention 11 minutes. I mean, just shouldn't be late even for 1 minute. Okay, since I'm gonna start at 8 a.m. Most of the guys are coming on time, so I should start on time. And F2, you start the library, and you need the resistor. So don't use the resistor in the library because you have some of the shortcut here. So directly use the resistor here. See this one. So my monitor is not mapped to the monitor there, to the TV correctly. So see, my mouse is at the little hand. You see that? But now it's projected to the resistor. So if I want to click the resistor on my monitor, on my laptop, it's somewhere else. So I select the resistor, and before I place it, I Control R so I can rotate it. I place it here, and I Control R, I place another one here, and ESC, I escape to quit that mode, and I place ground, and now I press F3 so I can wire things up. It's going to enter the wiring mode. Just single click. Oh goodness, cut the wire. F3, remember that, F3. Just make the connections. And now you want to change the resistance of the resistors and change the value of the voltage power supply. So right click and just put 5 in there and press enter. So get 5 volts. So for the resistor, should you change R or should you change R1? R. R1 is the name, right? So it is 3K. And this one is 2K. And you want to make a label for this node. Let's name it. Keep in mind, we want to name it. You are using this label. You'll see which one has been changed. It is actually this one. Right. Label net. And I just type Vout in there. Just give a name to that voltage node. So you are done with the circuit. So this one is equivalent to the SPICE code, except for the simulation command. I need to press .op and type .tran 0 second to 1 second, and every 0.01 second I want to plot a point. You don't need anything else because this circuit is the same as the SPICE code to describe the circuit, but you only need a SPICE code, a simulation code in this case. And now you're done. That's it. See, run the circuit, and you can see the same monitor, and right click, add traces, Vout, right? How do you want to present it, the figure? Cursor, and also make it smaller, right? It's a flat signal, you don't need that long. It's always 2 volts. Just make it smaller, and cursor, and put it here, and snapshot, and save it. So before save it, highlight the value you want to present to other people, okay, and highlight it. Save this one. So you're done for the simulation part for task 1, 2. So the simulation part. So when you put everything in one table, yeah, I mean for this one, we are organizing your data. Since you have 3 types of data, you need a table. So draw a table. You can draw it on the paper and take a picture, or you can directly create a table in the HTML, or you can create a picture in Excel and then do a snapshot from there. Make it into a picture. Okay. You have 3 columns, and you need your calculation, and you need your simulation, and you need your measurement, right? And just compare all these values for different parameters, for the currents, for the voltage. That's how you present your data. So the measurement is being done on the board. Make sure you understand this, right? If you need a current meter, just use a current meter. If you need a voltmeter, use a voltmeter. So have the meter readings as a picture in the report, and use a table for all the data. So now here's a new concept for the third one. Do a DC sweep for V1. The DC sweep starts from 0 volt and stops at 10 volts. Display the result of V1 and Vout on your simulation result. Show this in your report. And since I didn't mention that which method you should use, right? So how many methods we have for SPICE? 3. What's the first one? Text editor. The second one? Coding LTSpice, the .op option, right? The third one, just symbols from the library. And you can directly use the symbols from the library. It's a good practice since we are not going to use a lot of SPICE in the future. Directly use the symbols, which is fine. Do a DC sweep for V1. So it's still the same circuit. And now I'm going to open that circuit, which is this guy. DC sweep means I'm not do the analysis in time domain, but I'm doing that in voltage domain. So you just need to change the command here. So it's not a time domain analysis, which means the x-axis won't be time anymore, but that will be a voltage. So it's going to be dot DC. So actually you have a table here, I have a GUI to let you put the data in there. But we are doing a SPICE coding right now, so let's just code it up. So it's dot DC, which is telling SPICE you are doing a DC analysis. And you are trying to do a DC analysis over V1. And you want to start the V1 from 0 volts and stop at 10 volts. And every 0.01 volt, you want to plot the data point. So which means you are start increasing the voltage for V1 for the power supply. And now after that, after the linear, you actually give a linear increase for the voltage supply, the DC power supply. And after you give that value to the power supply, you are probing the parameters changes in the circuit, like VL, like the current. So you can plot all this data in a curve. So now this is a DC sweep command. As a V1, I'm sweeping V1 from 0 to 10 volts. And every 0.01 volt, I plot the data point. And click OK. And run it. So let's probe V1 first. And you can let me know if this makes sense. What is in there? I just probe the V1, right? And I sweep V1 from 0 to 10 volts. Okay? And I probe it. And I see something like that. So what's the x-axis? Volts. And what's the power supply for x-axis? What's the data come from? Where does the data come from? Of V1, right? So x-axis is V1 because I'm doing a DC sweep and it's going to show up on the x-axis. That's a variable I'm changing. Okay? And what's the result? What is the result for this DC sweep? I'm probing here. If I'm probing V1, which means I'm testing V1, so V1 will be the result. So V1 will be the y-axis as well. So it's actually a linear curve. X is V1. So when V1 is changing from 0 to 10 volts, on the y-axis, your V1 is changing from 0 to 10. They're both V1. And that's the input, right? You are giving an input, or you are giving a stimuli to the circuit. And now you are testing the result. I'm probing VL. And your VL is a blue curve here. And you can let me know if this makes sense. Why is that? Half of V1 all the time. Because it's a voltage divider, it's not half, it's 2/5, right? 2/5 of V1 all the time. And now you can look at the voltage source. I'm giving 5 volts to V1. And did you see anything about 5 volts in the result? And is this affecting the result? 5 volts here. No. You can give 0 volts. Doesn't matter because you are doing a DC analysis, it's going to sweep V1 anyway. So it's going to ignore that whatever DC value you put in there. It's not affecting anything. So now I put 0 volts, I simulate, you're going to see the same result. See, I just simulate it and you see the same result. Whatever V1 is, VL will be 2/5 of V1, right? Because the resistance share equals to the voltage share. Because this is 2/5 of the entire resistance. So all the way, it's going to be 2/5 of the entire voltage. So now this is a DC sweep. Now let's see what I ask you to do here. So DC sweep, show the simulation. Yeah, I just need the simulation for this. And then task 4, the power consumption of the circuit, which is P is the power equals to V times I. So voltage times current is a power supply of the entire circuit. So what's the power consumption of the circuit, both in theory and in real life? So here's the strategy. When you are trying to test the power of the circuit, power consumption of the circuit, where do we want to test? In the simulation. For example, in the simulation, if I'm not doing let's just come back to do a trend analysis, 0 to 1 and 0.01, and I give 5 volts to this guy. So this is 5 volts circuit. I'm trying to get the power consumption of this one. I simulate it. And you want to get the power consumption. So you know it's 5 volts. And when you are testing the current, I mean, even though you can get the same current all the way, everywhere in the circuit, but usually what you do is you test the current of the power supply, because all the power is coming from the power supply. So whatever current coming out from the power supply times the voltage of the power supply will be the power consumption. So which means the power supply is providing 5 volts, and all the components in the circuit is sucking whatever current from the power, and times the voltage of the power supply will be the power consumption, because all the current is being delivered to all the components. So this is how you can get the power from there and compare with the simulation calculation and the measurement for this task. And you have the last one before the interview, right? Before the little interview here. So make sure you can get it done probably 30 minutes before the end of the lab. Calculate the current and V out of the following circuit. Verify the calculation using simulation multimeter measurement on the board. So see that you have a 5 volts, you have a minus 5 volts power supply. How can you implement this in both simulation and on the breadboard? It's not 10 volts. You need a minus 5 power supply to the circuit. Yeah. So I draw this schematic in LTSpice. Doesn't mean that you can directly use this one for the. This is just a schematic. It's not a real circuit. It's not going to work. Okay. So the way to do that is, I'm just showing you this is a 5 to minus 5 power supply, nothing else. You cannot, you don't have this power supply in the library. So what you want to do is, remember in the homework, do we have this in the quiz? Probably not. Yeah, in the homework. So let's start a new schematic. So before doing anything, save it as task 5 to the desktop. And you need 2 power supply, one here, right? And you need to short the middle one and ground it, right? So, and then 5 volts here, 5 volts here. So here will be plus 5 and here will be minus 5. So you can provide this to the circuit. And now let's do it. One resistor, the second resistor, and connect them together. Is that a weird circuit? Yeah. 10K, 1K. All right, you don't have to use 10K, 1K. Actually, I don't recommend 10K, 1K. You can use 2K, 2K, 5K, 5K, doesn't matter. Just because this one is a voltage divider will make VL super tiny. It's gonna be 1 volt or something. But I think this will work. 10K, 1K. And we name the output to be V out here. And we do a simulation in the time domain. Right, simulation. So now let's see what are the questions. calculate the current and volt and VL. So what's VL for this 10K, 1K example? So what's the entire voltage drop? What's the total voltage drop across the circuit? 10 volts. This is from +1 to -1, so totally 10 volts drop entirely in the circuit. And this guy is taking 1/11 share of the resistance. You agree with that? And can you directly use 10 times 1/11 to get VL? Why not? So whenever I'm testing, this is a really good example actually. So when we directly use entire voltage drop times the share, we usually can get the VL, right? But this time we cannot. The reason is the other terminal, the VL of this resistor is not 0. It's -5, right? Did you get that? So which means the voltage drop across R2 doesn't equal to VL. Previously, you can do that because the voltage drop here across this resistor equals to VL, so you can directly do that, right? But now here is not VL. But what we want to get is actually VL. But if you just directly use the voltage share, you are getting a drop across R2, but not VL, right? So you can still do that. It's not a problem, but there's probably another better way to do that in case you are not getting any errors in there. So directly get a current first in the circuit. Get a current first. What's the current? So it's 10 volts totally, and the total resistance is 11K. So 10 volts divided by 11K, you are getting almost like 1 milliamps, probably 0.9 something milliamps. You get a current, and you can use the current times 1K, and then you are getting something close to 1 volt. And what's the voltage here? -5. And you get a voltage drop across R2 to be, for example, 1 volt. So from -5, you increase -5 by 1 volt, and you reach VL. So which means VL will be -5 plus 1. It's not 1, but close to 1. Okay, it's going to be something around -4 volt. So VL will be something around -4. So you can do a test. So build up the circuit like this in LTSpice, do a simulation. Let's run it, let's see. So here's the circuit. And do this, scroll the mouse. And let's see, I'm gonna probe this guy. And it is -4. Well, close to -4. Okay. So do a simulation and do a measurement as well. And you need to know, practice how to build up a double power supply in there today. Okay. I'll help you out. Any questions? Anything? Hope you guys can get it done, get all the 5 tasks done 30 minutes before the end of the lab. So you can, if you leave, I'm going to give you an interview, quick interview on the operation of the equipment. Okay? You can practice a little bit if you are not confident about that before you do the interview. All right.